is here. No coffee. Oh, all right. But anyhow, Tedward, it's always a great pleasure to be able to introduce a student when they finish their PhD. You know, for those of you who aren't in academia, as professors, we actually don't graduate that many PhD students in our career. It's actually a fairly small number, and so it's a big deal, right? But Tedward is actually a rarity too, because in the College of Agricultural and Life Sciences, we generally only bring students in when we have funding secured for them. And Tedward came to do a PhD without any funding. And he TA'd for 2 years, then got a NASA fellowship, and then has done a mix of different things for this last year, 6 years, to finish up the PhD. It takes a little bit longer when you don't have funding to do that. So it's a real testament to his perseverance to actually be able to do this. And so it's really a great pleasure to have had Tedward. And he continued some work that we had started with a previous PhD student in my lab. And it's really great because these urban environments are the places that we live. So just a couple of other things about Tedward is he also did a Master's of Biometry concurrent with all of this. He's actually already defended that. He's not going to present that chapter. He's going to present the 3 main chapters from his PhD dissertation. And he's also gainfully employed. He has been working half-time for the biometry program over the past almost a year now, and will be going full-time for them, teaching the Bio 571, 572 classes, and working as a consultant. Those of you who know Nick Coyler's similar type of position as that. And so Tedward is one of those people who has actually managed to transition into an actual career right away. So that's another thing, because we always, it's like your children, you know, you're always worried about what they're going to do. So I'm very proud of Tedward, and look forward to hearing your questions and comments on his PhD. Tedward, take it away. He's got his whole family here too.
Actually, not my whole family. There would be 20 of them here, but my parents are here.
He's got a portion of his family.
Yeah.
One of so keep your heckling down.
Thanks everybody for coming. I've been thinking about what to say for this talk for 6.5 years now, so I really appreciate you all taking an hour of your life to listen. So urbanization is one of the major trends of our time. By the middle of the century, more than 2 out of every 3 people on the globe will be living in a city. And many of these cities are relatively small ones, like ours here in Madison. And although cities only cover less than 3% of the land's surface, they have a disproportionate effect on our well-being as a species. Millions of people a year die early from smog-related illnesses, which are exacerbated in the urban environment. Massive heat waves that are becoming more common are made worse by the urban heat island effect, a phenomenon where the center of the city is much warmer than its surroundings due to the built-up surfaces there. And Madison, even though it's a small city, is no stranger to this effect. But the good news is that by smart design in our urban environment, we can ameliorate some of these negative effects of urbanization. One of the challenges of the 21st century is to figure out how can we make our cities more pleasant places to live. Many cities around the country have been spending millions of dollars planting millions of trees in an effort to try to capture some of the ecosystem services and benefits that trees provide, such as storing and sequestering carbon, improving air quality, reducing the urban heat island effect, reducing stormwater runoff, reducing noise pollution, reducing electricity use, providing habitat for wildlife. And also trees are just really beautiful and nice to have around. The smell of apple blossoms in the springtime is one of my favorite things about trees in the city. So if trees are so great, why aren't they everywhere in our cities? I guess the obvious answer is that cities are built for people, not for trees. That's what forests are for. But also, trees have a number of disservices and costs associated with them. They interfere with our utilities and our infrastructure. They increase water consumption, which is an issue in cities like Los Angeles. They're costly to maintain. They create allergens and volatile organic compounds. They drop branches on the hood of your car, breaking your windshield. They reduce solar access. Not only do they have these disservices and costs, but it's also just hard for trees to grow in the urban environment. Roots are being disturbed by construction. Your branches are getting hacked off to make way for power lines. The soil conditions are very challenging. And sometimes somebody comes and just whacks off your whole crown. That makes it very hard to grow. So when we're looking for the answer, it's just not quite that simple, and it's not quite that easy either. Generally, I'm interested in the relationship between peoples and trees in the urban environment. And it breaks down to 3 key questions. Where are the trees? Because our relationship with them depends on the spatial context. 2, what are they doing to us? What are the ecosystem services and disservices that trees provide for people in cities? And 3, what are we doing to them? How does the urban environment that we've created alter how trees function? My 3 chapters correspond roughly to these 3 questions. First, where are the trees? We mapped urban tree canopy cover for the state of Wisconsin. Second, what are trees doing to us? We looked at how trees in Madison affect building energy use and the associated carbon emissions. And 3, what are we doing to trees? We used remote sensing to estimate tree canopy, tree height growth, and then looked at how the urban environment can affect that. I'm going to go relatively quickly through chapter 1, spend a little more time on chapter 2, and then more time yet on chapter 3. So first, where are the trees? So where trees are is important. It's going to tell you whether or not you need to prune it for access for power lines. It's going to tell you if it's too close to your house, you need to prune it away. If it's blocking sunlight in the winter time, or if it's giving you shelter from the wind. All of the ecosystem services and disservices that trees provide are a function of where they are in the environment. So mapping them is important. Our goal was to make tree canopy maps for all of the urban areas of Wisconsin. We wanted to systematically test a number of things. First, we tested 2 types of imagery: NAPE, which is 1 meter aerial photography put out by the USDA, and Spot 6 imagery, which is satellite-based imagery. It has 6 meter spatial resolution, but that can be hand sharpened to 1.5 meters. So they're both comparable in resolution, but one's from airplanes, one's from satellites. We tested a pixel-based approach to classification with a segment-based approach. Segmentation is basically taking pixels in an image that are close in space and also similar spectrally, grouping them together into segments or objects, and then performing the classification on those segments. And we also tested a few machine learning algorithms. Our basic workflow was to take our different images, extract the training data, add additional features such as NDVI and texture. If it was a segment-based approach, we would do the segmentation, testing a number of different segment sizes, all the way up to 105 meter squares. Then we would add additional features for the segment, so basically calculating what's the mean of the red band within this segment, or the maximum of the red band within the segment, for example. If we were doing the pixel-based approach, we added convolutional features, basically took a moving window of different radii around the image and evaluating different functions in that window, the minimum, the maximum, and the mean. This provides basically spatial context for the pixel, what its neighbors are like, which improves the classification. We then perform feature selection, train our classifiers, support vector machines, generalize boosted regression models in random forests, and then we assess the accuracy. So just really quickly, the key highlights from the results. First, NAPE imagery outperformed this spot satellite imagery in every single case, which is really nice because NAPE is freely available, whereas spot you have to pay for. And also, NAPE is acquired every 2 years across all the lower 48 states. So it's really nice that not only the better imagery is also the one that's less expensive. This figure shows in the 3 different panels are 3 different classification algorithms. On the y-axis, we have our agreement with our reference data set, which was Google Earth imagery. And on the x-axis, we have the pixel versus the segment-based approach. You can see that if you just take your original 4 bands, red, green, blue, and near infrared of the NAPE imagery, and perform the classification, you get an agreement with Google Earth of around 80%, but it varies by classifier. If you do the segment-based approach, you can see that your accuracy is a function of your segment size. So we have relatively higher accuracies at segment sizes of around 15 meters squared, and then it drops around 20 and 30, and then increases again to a maximum around 60. So this shows that it's important to, when you're performing segmentation, to test a wide range of different possible parameters so that you can find the best parameters, and that also there might be different local maximums at smaller sizes and larger sizes, potentially corresponding to the sizes of objects in the actual image. If we perform feature selection on the segmentation approach, we see an improvement in accuracy, as you might expect. Comparing that to our convolutional pixel-based approach, we see that adding these convolutional layers to the pixel-based approach greatly improves accuracy. And then with feature selection, the pixel-based approach can perform just about as well as the best segment-based approaches. All of these maps in Madison had agreements of around 85%, and they tended to look, for the most part, very similar to one another. There were, however, a fair number of errors, and we wanted to figure out what's driving this disagreement between our maps and the reference data. So one of the things we looked at is how does the distance that our reference point is to the edge of a new land cover affect the accuracy. So, for example, our reference point landed in the middle of a forest. The distance to the nearest edge, new land cover, might be very big. So it would be out here on the x-axis, a large distance. But if our reference point fell on the edge of like a tree canopy, and then 1 meter away was a street or a grass, it was a very low distance, so it would be here. You can see that the median distance to an edge in an urban environment was about 5 meters, so very heterogeneous place, even with relatively high resolution imagery of 1 meter. And that this distance is really a big factor in what's driving this disagreement with the reference imagery. But urban forests and forests in general aren't managed just at a pixel level, but they're managed at larger scales. So we wanted to test what is the level of agreement on an area basis of our maps with our reference data. So we took an area, we said what is the percent tree cover according to our map in this area, and what is the percent tree cover according to Google Earth in this area. And you can see that as the area that you're considering increases, your disagreement between the reference and our map decreases, which is kind of nice. If you're about the scale of the Landsat pixel, which is about the size of a house parcel, you're going to be disagreeing on average about 10%. And when you get to the scale of a city block, it goes down to about 6%. We then took our method in Madison and extended it to the state. The overall accuracy went down to about 79%. And then with partners with the DNR and the U.S. Forest Service, this map was eventually uploaded to iTreat Landscape. which is a tool that can be used by anybody to look at how the tree cover in their city. So here is, for example, Green Bay. You can go to Green Bay, you can look at how does tree cover vary by neighborhood. And here's an example of that in Kenosha. So key conclusions, contributions of this chapter. One is that native imagery is very useful and it does better than spot. The pixel-based approach can perform just about as well as a segment-based approach. The errors in our method are largely driven by the heterogeneity of the urban environment, but that if we evaluate accuracy at larger scales, that becomes less of an issue. And this is available for use via iTree Landscape. If you would like to read more about this, you can check out a paper that was published in Remote Sensing of Environment with all of this work. So what are the next steps? Change detection. This is, I'm working with the DNR now on a project looking at how, using this method to look at how tree cover has changed through time. This is from southwestern Milwaukee County in 2005. If we look at the native images through time, you can see this development happening. Houses are being built, trees are being planted, and they're growing. And there's a lot of land conversion happening. You probably didn't notice, but if you had looked in the southeast at that patch of forest, you would have seen that up until 2013, our trees are looking very nice and green. But then after 2013, there's a number of gray pixels that are appearing. These are dead and dying trees, probably due to the emerald ash borer. So emerald ash borer is an invasive beetle that has recently arrived in the state and it's decimating a lot of our ash trees. So in the last decade, our forest has had a lot of change occur, and I think that this method that we developed will be really useful to helping to quantify just the nature of those changes. Okay, that's where are the trees. So now that we've talked about that, I'm going to be talking about what the trees are doing to us. So like I said, trees provide lots of ecosystem services and disservices for people. This is a table from Pataki et al. In 2011, where they looked at services and disservices, but not just listing them, also putting out their potential magnitude and our level of uncertainty around them. The effect of trees on net greenhouse gas emissions is the only one that appears as both a potential service and a potential disservice. And its magnitude is moderate and its uncertainty is quite high. I'd argue it's the most uncertain because it appears both as a potential service or a disservice. Now, we all know that cities are big emitters of greenhouse gas emissions and that a lot of them would like to do whatever they can to reduce those numbers of greenhouse gas, the amount of greenhouse gas emissions. And one of the ways they do that is by planting trees. But how do trees reduce greenhouse gas emissions? The first way they do is just by growing. By growing, trees sequester carbon from the atmosphere and store it in their bodies, which reduces carbon concentrations in the atmosphere. But also through our management practices, planting, pruning, chipping, removing, grinding stumps of trees, all of these uses fossil fuels, which contributes to greenhouse gas emissions. And third, trees alter microclimates. By altering microclimates, they affect building energy use and the carbon emissions associated with that building energy use. How is it that trees alter microclimates? Three primary ways. First, via shading, reducing wind speed, and evapotranspiration. In the summer months, the sun rises up high overhead, and the trees near your house can provide nice shade, blocking the solar radiation, so your house doesn't heat up as much. You don't have to use as much air conditioning to stay cool. You're not using as much electricity, and so there's less carbon being emitted from the power plant. In the wintertime, the sun rises more to the south. Those trees, especially the ones to the south, are going to be blocking that solar radiation, which is actually not a good thing because it means you need to use more heat to keep your home at a comfortable temperature. So trees in the winter can actually increase heating use and carbon emissions from that. even though trees, a lot of them, the deciduous ones, lose their leaves in winter, they can still block around 50% of the solar radiation, which is a significant amount. Trees also reduce wind speed, which can have a lot of complex effects on building energy use. But in general, by reducing wind speed, the demand for heating goes down and the demand for cooling increases. Via evapotranspiration, trees suck water out of the earth, pump it into the atmosphere, which provides cooling, reducing the need for air conditioning in the summertime. So what is the net effect of trees? We can see that shade increases heating demand, but decreases cooling demand. When there's less wind, heating demand goes down, but cooling demand increases, and evapotranspiration drives cooling demand down. So these arrows, you can see there's a lot of them, and they're going in opposite directions. So getting the magnitude of these effects correct is really key if you want to figure out what is the net effect of trees on carbon emissions. If you read the papers on this topic, you would see that it appears to be very clear that trees are decreasing carbon emissions from building energy use. This paper from a couple of years ago showed that for every state in the union, trees are shown to be reducing carbon emissions. But it just didn't seem like that quite made sense to me in a cold place like Madison, where we have a much higher demand for heating than we do for cooling. So the effect of trees via shading on cooling is necessarily going to be small because there's just not a lot of cooling demand in the first place. And there's going to be a fair bit of demand for heating. So if shade is increasing our heating more than our cooling, how is it that trees are reducing carbon emissions in a cold place? These past studies, through simulation, have in their models that by reducing wind, that's drastically reducing the amount of heating needed. So it's mainly the way that wind is modeling that's driving that relationship. But as noted in the Pataki paper, that's actually highly uncertain. The effect of wind is really complicated and difficult to model, and it has to necessarily be simplified. And it's based off of not exactly representative data sets. The effect of evapotranspiration also tends to be pretty optimistic. So there really is a lot of uncertainty with regards to this effect. This is a really not so great screenshot of a photocopy of a journal article from 1982, which is sort of representative of just the quality of the data we have on this. This is the only paper that actually has real empirical data on building energy use for the effect of trees in a cold place. So the major contribution of this work is that we actually collected empirical data to test some of these models. If you go to the Madison Gas and Electric website, type in your address or the address of the chancellor, you can see, on average, how much gas they're using, which is related to heating, or electricity they're using, which is related to cooling. We did this for about 21,000 homes in Madison, and then we linked that energy use data to every house. We then took that space around the house and divided it into 8 regions. North, south, east, west, near, which is within 20 meters of a house, and far, which is between 20 and 60 meters of a house. We then overlaid our tree canopy map from Chapter 1 and calculated what's the amount of tree cover in each of these regions. We then modeled the total carbon emissions from the energy use as a function of tree canopy cover in each of these regions, while controlling for building covariates such as size, number of floors, number of garages, that type of thing. And then we had a random effect for neighborhood, which could potentially control for historical factors or cultural factors. We built separate models for the carbon derived from electricity, which again is cooling, related to cooling, for carbon from gas, which is related to heat, and then total carbon emissions. What did we find the effect to be? So if you just take all the tree cover in that near region and you look at what's the association with total carbon emissions, you can see that trees have a very clear, cause a very clear increase in total carbon emissions. This x-axis can roughly be interpreted as the percent increase in carbon emissions. It's not 15%, but 0.15%. So a very, very small amount, but also very clear effect or association. We then split up the tree cover into our 8 different regions and the carbon into the different sources. Electricity, which again is cooling, gas, heating, and then total carbon emissions. You can see that tree canopy cover generally decreases electricity and the carbon from electricity. It generally increases carbon from gas, and mostly those effects cancel out when you look at total carbon emissions, with the exception of tree canopy cover in the near east. So what's happening here is basically in all these other regions you have this cooling benefit of tree canopy cover, with the exception of the near east. This might be due to the fact that in the summer months when the sun rises in the east and you're getting the shade from those trees, that's actually not a time where you have a lot of cooling demand because it hasn't warmed up yet. And so they're not giving you much of a benefit, but they still appear to be causing a heating penalty, which in effect is increasing your total carbon emissions. If you look at typical tree cover around a typical house in Madison, over the course of a year, it could be increasing carbon emissions by several tens of kilograms of carbon a year. This is sort of on par to like maybe like a cross-state road trip you might take in your car. So this is interesting, but is Madison just an anomaly? So I looked in more detail at this paper by Akbari from 2002, and in what I really think that the title of this paper should have been is that, on average, shade trees reduce building energy use and carbon emissions from power plants. Because if you look in detail at their methods, you can see that there's actually, their model has a fair bit of geographic variability to it. So I took their model and updated it with some current energy emission factors and predicted the effect of tree canopy cover on building carbon emissions for every census block in the US, which you can see here. So the key things about this figure. First is that the magnitude of the potential cooling benefit of trees is much higher than the magnitude of the potential penalty, or sorry, the decrease in carbon versus the increase in carbon. So this is what's driving that, on average, trees would be very beneficial. But it's still the case that for around 40% of people in the US, they live in a place where trees, according to this model, are increasing carbon emissions. Generally, this follows the climatic gradient from hot south to cool north, but there's also some splotching around here. And this is mostly due to different energy mixes in the electricity that they're used. So if you look at New York, for example, it has a very high, trees are causing a big increase in carbon emissions there. And that's actually because they have some of the cleaner electricity in the country. So because they have clean electricity, trees, by reducing air conditioning loads, is they're not having that big of a benefit, because there's not that much carbon in the electricity there, but they're still causing that increase in heating. So on balance, they actually have kind of a not so great effect there. So it's one of but what about sequestration? Trees are growing, right, and they're sequestering carbon. How does that compare to the amount that they're causing to be emitted? If you take sort of a medium-sized ash tree, it might sequester around 34 kilograms of carbon a year. And that same tree in Madison, according to what we found, would only increase carbon emissions by about 10 kilograms of carbon a year. So this is good. Sequestration is much greater than emissions. It's really not that big of a deal. But actually, there's a key distinction to be made. That's that sequestration is a transfer from the atmosphere to the biosphere. So once that tree decays, dies, that carbon is going to go back up into the atmosphere. Whereas when we use fossil fuels, that carbon was fossilized, now it's in the atmosphere. That's not going to be easily reversed anytime soon. One way to possibly get around this would be to use the trees that have grown for building to try to prevent that decay. So what's the significance of this, the overall takeaway, the significance of this research? Contrary to what a lot of other people have found based off all these past simulation studies, using real energy use data, we found that in Madison, it appears that trees are increasing carbon emissions from building energy use, and that that's likely the case for much of the country. This is a paper from 2002 looking at Wisconsin's urban forests, showing that trees are actually avoiding carbon emissions. This again is from simulation. So by using real data, we've shown that that's probably not the case. And we need more studies like ours across the country so we can figure out where it is that trees are causing increased emissions and where they're decreasing emissions. But the second key takeaway is that the effect of trees is actually very, very small, like less than 1%. So if you want to plant a tree, you should definitely plant a tree because they're beautiful, wonderful, great to have around. And know that you're not really causing the climate crisis, but you should also know that you're not saving us from it either. And when you plant a tree, you should just maybe consider where you're going to put it in the ground next to your house. Maybe not on the east side. This work was published in Environmental Research Communications. If you'd like to learn more, you could check that out. Okay, we're moving right along. Very good. We've talked about where the trees are, what they're doing to us. So next is, what are we doing to them? So like I said before, it's very hard to be a tree in the city. I don't know, these trees are awesome. They're the lilacs over there. They just constantly are struggling to survive, and yet somehow they persist. It's pretty amazing. This is a tree over on Monroe Street with construction, its roots getting totally disturbed. I don't know if it's still alive. There's a tree that had to be pruned into a V shape. And then this tree was is by my house. It was doing very great, and then one day it got cut down. So it's hard to be a tree. But there's also been some really interesting work that has come out relatively recently that has shown that the urban environment can actually enhance tree growth in some cases. That was a paper from New York. This paper looked at used tree ring study from cities all over the world and found that trees closer to the city were growing more than trees farther away. And if you look around Madison, you can see evidence of trees doing really great. This is just a massive sycamore on the north side. This is one of our really wonderful big ash trees. And we also have many large honey locust trees. So even though things are tough, you can find some great specimens. So why do we care about tree growth? Well, all of these services and disservices that trees provide are a function of the growth, either directly, like sequestration, or indirectly, like once a tree gets bigger, it's going to be having a greater impact on its environment. So knowing how the urban environment is altering tree growth is key to understanding their effect on us in turn. Let me introduce you to some of the trees of Madison. This is the tree inventory data set for the city. We have a street tree inventory, which covers the streets, and then we have two neighborhood inventories. The Hill Farms neighborhood on the west side and the Atwood neighborhood on the east side. You can see that maple is the most common genus. That's Acer. It makes up almost 25% of all of our trees in the inventory data set. Then followed by ash, fraxinus, honey locust, tilia, which is linden, spruce, interestingly, not a very common street tree, but super common in the neighborhoods, oak. This is super cool. It tends to occur mostly on the near west side as a street tree, but not common elsewhere. And also there are these like patches of oak trees all over the city. You can see one there in Hill Farms. elm, arborvitae, fuchsia, Celtis, and then all the other trees. These are mostly smaller trees that I ended up not using in this part of the study, so that would be apple and lilac, for example. So there are key three genera that make up over half of all of our trees. There's maple, which is just really nice in the fall time. This is a street that has sugar maples planted on it, which obviously have very wonderful color. But the most common maple species is Acer platanoides, which is Norway maple. That is a non-native tree. It tends to grow kind of squat in stature, but it generally does well in the urban environment. The next genus is Fraxinus, which is ash. Ash, as I said previously, is under threat from the emerald ash borer, which has arrived in the last, it arrived in Madison, I think, in 2013. So a lot of these trees have either had to be protected with insecticide or been removed. And then third genus is Laditia, or honey locust. This is what I like to call the Calypso Cathedral, and I think that it should be a tourist attraction in the city of Madison. This is one block over from where I live, and it's just like the most amazing block of honey locust trees. So they're very tall. They have fine branches and fine leaves, and they're just really quite nice. So those are the trees. Also, in this chapter, we used two types of remote sensing technology to better understand the trees. First, we used airborne laser scanning, also called LiDAR. This is an active type of remote sensing where a laser pulse is sent down from an airplane flying above. When the light gets reflected, it records with sufficient intensity, it records the location of the objects below. So you can create a 3D model of the land surface. We also use imaging spectroscopy. This measures the reflectance of light from the surface at many different wavelengths, from the visible all the way to the near infrared. And from these, you can derive foliar canopy traits. These two technologies have been used quite extensively in forestry, but less commonly so in urban systems. I'm going to talk a little bit about LiDAR and then the hyperspectral, or the imaging spectroscopy. So here you can see in green are the LiDAR points that are trees, and gray are the other objects. LiDAR is really great at getting the canopy structure. So you can see this is a tree that has a big hole in it that you probably wouldn't be able to see from aerial imagery, but you can capture that with the LiDAR. We used 4 years of LiDAR data to look at growth of trees. And as you can see, in time, the pulse density has increased as the quality of the LiDAR has improved. This can cause some problems if you're trying to get at height growth. So this is a tilia tree. You can see that it's increasing in height through time. But because of the low pulse density in 2005, we don't really know where the top of this tree is. Is it here, where it was observed, or somewhere higher? So one of the challenges was, how do we correct for this low amount of, the low pulse density that we have in 2005? So we took trees like this oak that weren't growing, we subset down to just the first returns, and then looked at the center pixels, or sorry, the center returns, so that we avoided interference with other nearby trees. And if you look at this, you can see we have this, assuming that this tree hasn't grown, there's some maximum height that's been constant through time. And in this case, it was recorded in 2009. So in 2005, we have a lower height, and this is just due to sampling variability. We assume that it's just that there was less pulses, so we missed the top of the tree. We wanted to quantify what is the expected underestimation or bias that we would have from having low pulse density. So we resampled those points according to the number that we had before, and we can get another estimate of tree canopy height. we do this 1,000 times, resampling all these points, you can get an estimate of the mean bias due to pulse density. And also the variability due to that. We did this for dozens of trees for each of the major genera. We at every different possible pulse density. And you can see that as the pulse density decreases, the amount that you're underestimating height goes up. The magnitude of that effect increases sharply. And you can see that this varies significantly by genus, and it's a function of both tree canopy architecture and also branching structure. We then applied these curves to every tree to correct for this height bias. So in gray, you can see our observed heights, just raw from the LiDAR, and the gray line is a linear regression for those 4 points. So the slope of that line is the change in height through time, or the growth rate. The red points are our bias-corrected heights, and the red line is a weighted regression, where the weight is proportional to the number of pulses that we have. So starting on the right side here, you can see that this tree, in 2005, we had a very high bias for the height of this tree. If you were to just go along here from the other years, you see that it's not growing that much. So this bias correction bumped that point up to create a more realistic estimate of growth. The next tree from the right, we overcorrected our bias. We overcorrected for the bias, but because it was a weighted regression and there was a lot of uncertainty around 2005, the growth rate wasn't negatively impacted too much. The middle panel, it seems that maybe we undercorrected the bias, and then the two panels on the trees on the left, that bias may have been overcorrected, and the growth rate was estimated to be negative. So if you take all of these growth rates, the average growth rate was for all of our trees was around 13 centimeters a year. Some of these appear to be negative, and that's because of this overcorrection that I mentioned, but those are probably canceled out by some of those that were undercorrected that might have elevated growth rates. This is what these growth rates are then what we're going to be using as the response in our regression model. Okay. So next I want to talk a little bit about the imaging spectroscopy data. So we used data from NASA's Avarice NG, which is an imaging spectrometer flown on an airplane that in 2005 captured imagery over most of the city of Madison. And in every pixel of these images, you have a full spectra. And these spectra, which is the reflectance of light at many different wavelengths, contains information about what is inside of the leaves. And these things vary by species. So we collected a number, in addition to the imaging spectroscopy data and the foliar canopy traits that we derived from the imaging spectroscopy, we collected a number of other covariates that we thought might be related to tree growth. The initial height of the tree in 2005, what its genus was, whether or not the tree was a neighborhood or a street tree, did it have overhead utilities or not, what was the height of buildings and trees within 20 meters of a tree, what's the percent of impervious cover within 20 meters and within 100 meters of each tree, and then topography, and also our foliar canopy traits. We had a number of different hypotheses. We thought that neighborhood trees would grow faster than street trees, that trees without power lines would grow faster than those with power lines, that foliar canopy traits related to photosynthesis, like percent nitrogen and chlorophyll content, would be associated with an increase in growth, where traits, defensive traits and traits for structure would be associated with a decrease in growth. We thought that if you had a little bit of impervious cover locally, like you had a nice local condition, that might help save you from the negative effects of impervious cover more broadly. And and that also trees would grow up more in response to competition for light. So trees that are more open grown are going to be growing less than trees that are near other trees or buildings. We built a series of multiple linear regressions to test these hypotheses. We added fourth order polynomial terms for height because growth is a nonlinear function of height, and also various interactions that were consistent with our hypotheses. And we also fit models with genus included in it and without genus, because we wanted to look at how does the urban environment affect trees regardless of genus, and then also genus specific. So what are some of the findings? Growth rate is on the y-axis here, and the initial height is on the x-axis. So when trees are relatively short, they might be growing about 30 centimeters a year, which is about a foot. As they grow taller, their growth rates decrease as they're asymptoting in height. Neighborhood trees are growing much faster than street trees, but there doesn't appear to be much of a difference between trees that have overhead power lines and those that don't. Genus plays a big role in how fast trees are going to be growing. So if you just look at the marginal means of these growth rates, you can see that there's quite a lot of variability due to growth. Due to genus. And that if you look at the height by genus interaction, you can capture kind of a richer picture here. If you look at poplar and ulmus, which is elm, they're growing very fast when they're relatively young, but then they decline sharply in their growth rates as the trees grow to height. Compare that to pinus, which is pine. They have high growth rates when they're relatively short, but then they also maintain high growth rates even as they're growing taller, which makes sense since white pine especially is one of the biggest trees we have around, tallest we have around. If you look at the three key most common genera, you can see that when they're growing as neighborhood trees, they have very similar growth rates, but that when they're growing on the street, the maple tends to grow much less than ash and honey locust, Fraxinus inflaticea. So it could be that maple is more sensitive to the street environment than these other two genera. The foliar canopy traits derived from imaging spectroscopy contain a lot of information that can be used to create maps of growth, even if we don't have the information, the inventory data for genus. And these traits had significant effects on growth. Chlorophyll, as we expected, was positive. Total phenolics and lignin were negative. But surprisingly, nitrogen was also negative. It could be that in the urban environment where trees are already saturated for nitrogen, that it's not going to have a positive effect on growth. We've split this out by genus. We can see that there's quite a lot of variability across genus, but that there are some interesting significant effects, like for example, elm, ulmus has a very strong association. Chlorophyll for elm has a very strong association with growth. The height of the tree's surroundings affects how fast it's going to be growing. So open grown trees here are growing much less than the trees that are surrounded by other buildings and trees, up to a point. We didn't include in any of our data trees that might be completely overtopped, so we don't see a negative effect of too much competition for light because of that. Impervious cover generally decreases growth rates. On the x-axis we have the impervious cover within 100 meters, the broader scale, and the color is the more locally. You can see that the green line is if you have low impervious cover locally, that growth rates can be maintained relatively high, even if at high impervious cover more broadly. And if you look at neighborhood trees, the highest predicted growth rates actually occur for trees that have low impervious cover locally within 20 meters, but then have moderate amounts of impervious cover more broadly. This could be potentially due to the urban heat island effect, of broader environment warming, broader impervious cover warming the environment. This shows the predictions of our models. You can see generally that trees in our neighborhoods are growing faster. trees where there's a lot of impervious cover are growing less, and trees on the outskirts where there's younger development and the trees are generally shorter are growing more. So what are the contributions of this work? We have developed a method to estimate height for thousands of trees in a city, height growth. Foliar canopy traits derived from imaging spectroscopy can be used to make maps of tree growth when you don't have inventory data of the genus. And that the urban environment seems to affect growth, sometimes in unexpected ways. So I started with these key questions, and I hope that I have contributed in part to their answer. When we looked at where are trees, we developed a map of tree canopy cover for the state of Wisconsin, and that is available for people to use online. When we looked at what trees are doing to us, we showed that trees seem to be increasing carbon emissions for homes in cool climates. And that has implications for tree planting programs across the country. And we showed that the urban environment seems to be affecting tree height growth in ways that might be are generally negative, but not always so. And that we can use these to better map the ecosystem services that we depend on. I'd like to conclude with this quote, which I selected mostly because it's from a book about a guy who decides to go live in trees and never set foot on the ground again. But also because I think it speaks to the power of remote sensing, which was really key in my work to gaining insight into what's happening in the urban environment. And also because it speaks to the scientific method. It was kind of interesting for me to study organisms that I'm such a big fan of in a kind of a critical way, trees. But I think that by gaining a deeper understanding of our relationship to trees, I've come to love them more for who they are than who I want them to be. And I think that that's a good lesson for the future. So I'd like to say thank you to everybody who funded this work. It hasn't always been easy, but I do think it's pretty amazing that I got paid to do this research, and I'm very grateful for that opportunity. I'd like to thank my partners at the Wisconsin DNR, especially Dan, who's in the audience here, Andy Solman and Laura Lawrence, too, who helped a lot with Chapter 1. And definitely the University of Wisconsin. I'd like to thank Phil, most of all, for being my advisor. I've learned a lot from you in the last 6.5 years, and I'm very grateful. I think you are a great example of a scientist, and we have a really amazing lab group, and it's just, I feel very lucky to be a part of that team, and I thank you. I couldn't be here without you. I'd like to thank my excellent committee. I think each of you have really helped me to become a better scientist, and I'm very grateful for that and all of our interactions. I'd like to thank the lab. You guys are awesome. I love learning from you. And I'd like to give a special thanks to Ben for a lot of his work with the field work, and also always remembering my birthday. And a special thanks to Adam, too, who sits behind me in the office and has really, I've learned a lot from him. My Blender animations were inspired by him insisting that I do better. And I'd like to thank all of you all for coming very much, especially my parents. Thank you. And my in-laws too for coming, that's very nice. And then my daughters and my wife, Bridget, so thank you. I wouldn't have been here without Bridget. I wouldn't have even applied to the University of Wisconsin if she wasn't from Wisconsin. And I'm really happy that I ended up here. It's been really great. It's been, yeah, I've learned a lot, and thank you. So that's it. Any questions?
Clear the onions out of the room.
What's your favorite tree?
My favorite tree, individual tree, that I wanted to show a picture of but I didn't get to is actually a tree that I planted in 2011. It's a sycamore, and I planted it at my parents' house. And every time we go to visit, we take our picture in front of it, and it's now as tall. It was this tall when I pulled it out of the ground, and it's now as tall as their house. It's pretty amazing to see. Yes.
We have two questions. So, in addition to the effect the tree might have on heating and cooling, there's also, if you consider the carbon that's expended in initially growing it in the nursery and planting it and maintaining it, there's a lot of carbon
Yeah.
expended that is a negative thing
Yes.
as well, right?
Yes.
Okay. So that's not accounted for. Can you estimate that, or have other
Yeah,
people
so it's
estimated
kind of,
that?
yeah, I didn't talk about that, but it's kind of, actually there was, so in 2002, this guy named Nowak, who was one of the main researchers on this topic, looked at the emissions from management. And as you said, basically, without this building energy use thing, and that all aside, trees are, because of all of the management associated with them, are increasing carbon emissions. The magnitude of that, I think, is comparable to what I found here, like relatively small. It's the kind of thing where over short time frames, via sequestration, trees can reduce carbon emissions on balance, but over the long run, you put fossilized carbon into the atmosphere, and it's just going to be permanently increased.
And then the second question relates to whether it's possible, maybe the next person will come along and look at this data on carbon emission in the context of the quality of the house in terms of the way it's built. In other words, a more modern house with thicker walls, and we've got better codes now and things
Yeah.
like that. Could that strongly affect whether you have a net positive or a net negative effect? And I'm wondering if that could be pieced out. I mean, in Madison, we have some houses that have nothing in the walls.
Right.
Because they were built 100 and some years ago, and we have others that are built much, much better in terms of energy use.
Yeah, no, I think, so in general, I think better built homes and recent ones, just the magnitude of the effects goes way down just because they're better insulated. So they don't need as much heating and they don't need as much cooling. But I think when it comes to if it's going to shift the balance, I think that just more is dependent on the design. Is the building designed for passive solar gain or not? Where are the trees?
Can your data be further used to parse that out?
Yeah, I think so.
And could you look at house orientation, one story versus two story, things like that?
Yes, it definitely could be. I chose to simplify the analysis for sure because it became extremely unwieldy. And also there is a ton of noise. Like the main driver of carbon emissions in buildings is the behavior of the people. It's not the trees. So finding an effect of trees was really only possible with a very, very large sample size. Other questions? Yes, Ben?
Kind of to follow up on that, by the way, Tedward, you're very thorough. Appreciate that. The people are driving more than the trees. My question is, in all the data you looked at, did you notice differences from neighborhood to neighborhood? Or is that kind of lost in the big data?
I didn't I didn't look in particular by neighborhood to neighborhood, but one of the probably the most striking thing is just the houses on the lake are using way more energy. Probably because they're bigger, but also because they're subject to the wind off the water. So, but no, to answer your question, I didn't see much difference. Yes, Will?
Can you talk about trees and urban agriculture and like the effect of trees that produce food and the way that relates to the bigger picture?
I didn't look at that. I think that it's, I mean, like I mentioned before, people don't like trees that make a mess. So like a lot of the trees that we have on the street, honey locust, they have tiny leaves that just get blown away. They don't produce seeds. A lot of the ash trees we have also don't produce seeds. So a lot of it is about like minimizing the stuff that's dropping, and so I think that's why we don't have a lot of food producing trees. People just don't like that falling on their cars. And it's just about like, trees are like they're like part of our garden, you know what I mean? They're more planted for like aesthetic reasons. So. Yes, Dad?
Ted, when you looked at this data and you've learned a great deal from all of this, as you look into the next 5 years, 10 years, 15 years, 25 years, 55 years, 105 years, what would you do based on what you've learned about trees and what they do to us and what we do to them and where they are? What would you change to impact the future in a positive way?
That's a very hard question. I knew you were going to give me a hard ball there.
What first?
I don't know. I think actually I would say that I kind of came into this thinking that because of the stuff that I had read previously, that trees really were a part of like solving climate problems and stuff like that, but I've kind of come to realize that it's not. They're nice, but they don't play that big of a role. And so I think just kind of being real about their effects, I think is key. I don't know.
So you would plant more because they're nice.
Yeah, probably, but also like I think it's important to think just the size of the tree, where it is. I also love sunlight, especially in the winter of Wisconsin. So planting trees not to block that is also important. Yes. Oh, one more question from the line.
So another big implication of trees in urban areas, and Milwaukee has spent time trying to justify it, is based on how they add to handling water. As we all know from the news in the last couple of days, water every year is becoming a bigger and bigger issue in the upper Midwest as rainfall is increasing. So again, could your data set be used by somebody who wants to maybe say, well, you know, it's kind of a neutral issue with heating and cooling, but maybe there's net positive benefits with water?
For sure. I think, and that's one of the great things about the LiDAR, which the high quality LiDAR became available in 2016 and 2017. With that, you could get a pretty good estimate of like leaf area or branch area, and that's going to be what's key thing in preventing, like reducing stormwater runoff and that kind of thing. So yes.
All right, let's give Tedward. So we'll give you a few minutes to think about your dad's question. Answer that.
It also is kind of associated, right? So
How's that?